This is a brief tutorial of the ideal gas law and some of the permutations of it, and a little bit on gas stoichiometry and chemical reactions. So if we look at Boyle's law, which we mentioned in our proportional gas law video, so if you're unfamiliar with those, look back at that one. It said that the volume was inversely proportional to the pressure at constant temperature and amount of gas. Charles's law said the volume and the temperature were proportional at constant pressure and amount of gas. If we look at Avogadro's law, we could say that the volume and the number of moles are proportional at constant temperature and pressure. If we combine those into one statement, we can say that the volume is proportional to the moles times the temperature divided by the pressure. But that's only a proportionality. We need to put in a constant to make that an equality. So converting that, we say volume is equal to nRT over P, where R is that constant of proportionality. And that's going to give us what we call the ideal gas law. If we rearrange it into its more familiar form, we say PV equals nRT. P is pressure, V is volume, N is moles of gas, R is our constant, and T is the Kelvin temperature. And so we're going to call R the universal gas constant. So we need to determine the value of that R constant. And if we assume our STP conditions, 1 mole of gas will be at 1 atm and 273 Kelvin with a molar volume of 22.4 liters. If we solve our ideal gas equation for R is equal to PV divided by NT, and we're going to substitute the values from above and figure out what R should be. So 1 atm times 22.4 liters divided by 1 mole of gas and 273 Kelvin. We get a value for the R constant of 0.0821 liters atmospheres divided by moles in Kelvin. Now, that means that if I use PV equals nRT and use that value for R, the pressures have to be in atms and the volumes have to be in liters. Moles in Kelvin will be the N and T units regardless. But if I change the pressure volume units, I'd have to have a different constant, which could be solved similarly like we did here. There are some values. If the units are changed, the R can be 8.314 joules per mole Kelvin. This version is popular in thermodynamics, which is the subject for a different presentation. But you get the same value, 8.314 pascals meters cubed divided by moles in Kelvin, and this one is in SI units for pressure and volume. Do some creative unit rearrangement, you can get the joules out of it, but I'll save that. You can try that on your own. If we want to use some more common laboratory units, we could use 62,400 millimeters of mercury times milliliters divided by Kelvin and moles. And those are some common laboratory units if you're using a mercury barometer and typical measuring devices in the lab for volume. So let's use the ideal gas law on a problem. What volume would 50 grams of ethane, C2H6, occupy at 140 degrees Celsius at a pressure of 1820 torr? Now remember, if we're going to use that value for R that we originally derived, the pressure is going to have to be in atm and the volume is going to have to be in liters. So the volume we solve for should be in liters. We're going to get those torr into atms. We're going to get those temperatures into kelvins. We're going to convert that 50 grams into moles. But we know it's C2H6, so we can use the molar mass there. So T1, 140 degrees Celsius plus 273 is 413 Kelvin. The 1820 torr divided by 760 torr per 1 ATM will give us 2.39 ATMs. Molar mass of ethane, 2 carbons mass plus 6 hydrogens mass. So 2 times 12.01 grams per mole plus 6 times 1.01 grams per mole will give us 30.08 grams per mole. So all that should be pretty straightforward. Now we need to get the moles. So our moles is going to be our 50 grams of ethane divided by 30.08 grams of C2H6 per 1 mole. That gives us 1.66 moles of ethane. Now we're good to go for our ideal gas equation. So we're going to use PV equals nRT, solve it for volume since that's what the problem's asking you for. So V is equal to nRT divided by P. Now we're going to plug in all the things we just converted. 1.66 moles times 0.0821 liters ATM per Kelvin mole times 413 Kelvin divided by 2.39 ATMs. Everything but the liters cancel, and we get 2.36 liters of ethane gas. We can also calculate density and molar mass of an ideal gas by rearranging the ideal gas equation using some substitution and some algebra. So if we start with our PV equals nRT, we can substitute in mass divided by molar mass, where molar mass will use that scripty looking M for moles, and we find that PV equals mRT divided by big M, which is molar mass. Then it's just a matter of solving for molar mass. Molar mass is equal to mRT divided by PV. So we need to know the mass of the gas to get the molar mass using this formula. We could also substitute mass divided by volume is equal to the density, capital D. So molar mass is equal to density times RT divided by P. So if I knew the density of the gas instead of the mass and the volume, I could still get the molar mass. Rearranging that for D, you can calculate the density of a gas assuming you know the molar mass. So density is equal to pressure times molar mass divided by RT. So here's one for the molar mass. A student collects a sample of a gas in a 0.220 liter gas bulb until its pressure was 0.757 atm at a temperature of 25 degrees Celsius. If the sample had a mass of 0.299 grams, what's the molar mass? I've conveniently given you ATMs in liters. We just need to get that 25 degrees Celsius into Kelvin, which would be 298 Kelvin. So molar mass is equal to mRT divided by PV. So 0.299 times 0.0821 liters ATM per Kelvin mole times our 298 Kelvin, which came from our 25 degrees Celsius, which we'd calculated before, so I didn't show that explicitly here, divided by the 0.757 ATMs and the 0.220 liters. We find all the units will cancel but the grams and the moles, and we get 43.9 grams per mole. If you look for real gases that are in that range, propane, carbon dioxide, or a couple of gases that are in that 44-ish grams per mole range, so that could limit your list of suspects if you're trying to identify the gas, if you can find out what the density is or the molar mass is. In this case, that molar mass in particular would let you know, or at least to let you eliminate certain gases as possibilities. Here's one for the density. Air is primarily a mixture of nitrogen and oxygen, and is often assumed to have an average molar mass of 29 grams per mole, since it's mostly nitrogen and to a lesser extent oxygen. Let's calculate the density at 25 degrees Celsius, or 298, and 1 atm of pressure. So again, the 25 plus the 273 is 298, just like before. Density is equal to pressure times molar mass divided by RT. So just plug and chug. 1 ATM times 29 grams per mole divided by 0.0821 liters ATM per mole Kelvin times 298. Everything cancels but the grams and the liters. So it's 1.19 grams per liter. But notice the volume unit's bigger. Normally we do density in grams per milliliter, but gas densities are often in grams per liter. Dalton's law of partial pressures states that the pressure exerted by a mixture of gases is the sum of the partial pressures of the individual gases. So assuming they occupy the same container, we can say that the total pressure is equal to the pressure of each component of the gas added up. So since they don't really interact much, that's our assumption with the ideal gas law, that the total pressure is just related to the total number of moles of gas, assuming constant temperature and volume, and is independent of any interaction between the gases, so the pressures just sum up. Now if we got 100 milliliters of hydrogen at 25 degrees Celsius, 3 ATMs of pressure, and 100 milliliters of oxygen measured at 25 degrees Celsius, 2 ATMs of pressure, and we force all that gas into one pressure, what would be the pressure of the gases? So since the temperatures and the volume stay the same, we know that the pressures just add together, and so the answer is just 3 plus 2 equals 5 ATMs, because everything's the same. It's just based on the total number of moles of gas. One of the more common ways to use Dalton's law of partial pressures is to subtract for vapor pressure of a liquid that we're using to collect the gas, usually water. The appendix in your textbook will often have a table of vapor pressures of water at various temperatures. What you would have to do is find the temperature of the water and then look up the vapor pressure in a table. So if we got a container of water here, the bottom is liquid water, but above that is some gaseous water, which I've kind of indicated in that sparse blue color because you can't normally see water vapor, but I want to make it visible in this case. So we have some fraction of that air above the surface of the water that's actually water. How much depends on the temperature. It's usually a small amount, but we still have to account for it if we want to be precise about our gas's pressure. So let's say a sample of hydrogen was collected by displacement of water at 25 degrees Celsius or 298 Kelvin. The atmospheric pressure was 748 torr. What was the pressure of the dry hydrogen exerted in the same container? So if we look up 25 degrees Celsius in the container, we would find that vapor pressure is 23.8 torr. And you'd have to look that up. There's no way to memorize all the possible values. So we find that the dry gas, the dry hydrogen, with the water vapor excluded from the pressure measurement, would be our pressure reading, 748 torr, minus the vapor pressure of the water, in this case 23.8 torr, for a total of 724 torr of pressure from the hydrogen gas. And you can work any of a number of different gas law problems where you collect things over water. You just have to make sure you do that subtraction for the vapor pressure of water, and then you can work the gas law problem normally in the way we've worked the gas law problems up until this point. Partial pressures and mole fractions. Since we assume that the pressure is totally dependent on the moles of gas at constant volume and temperature, we can just use moles and pressures in this case. So if the N sub I is the number of moles of some gas I exerting a partial pressure P sub I, then we can say the partial pressure of gas I is equal to chi sub I, which is the mole fraction. It looks like a little x, but it's a Greek letter chi, times the total pressure of all the gases in that container. your values will range from 0 for the mole fraction to 1, 0 meaning there's none of that gas in there. 1 means all the gas in the container is that. Those are two extreme cases. Your mole fraction is usually going to lie between that, between 0 and 1. Mole fractions don't have units, so don't write any. And it's not a percentage, so don't write any percent signs. So the chi sub I is the mole fraction, which more properly would be the partial number of moles divided by the total number of moles in the container. But since we're working gas law problems, pressures are much easier to measure, so we can work it out with pressures. And that's more convenient than moles in this particular instance. So what are the mole fractions of nitrogen and oxygen and air when their partial pressures are 160 torr for the oxygen and 600 torr for the nitrogen? So the total pressure will be the pressure of the nitrogen plus the pressure of the oxygen, which is our Dalton's law. 600 plus 160 is 760 torr, or 1 atm. Mole fraction for the nitrogen will be partial pressure of the nitrogen divided by the total pressure. So that'll be 600 divided by 760, or 0.789 is our mole fraction. Noticing the torr cancels, leaving us with a unitless number. Mole fraction of oxygen is the same idea. Partial pressure of oxygen divided by the total pressure, or 160 divided by 760, torr cancel, giving us 0.211. Again, no units. So if we use our information from our previous problem and assume that the mole fraction of oxygen in air is 0.211, if the total air pressure were only 250 torr, what's the partial pressure of the oxygen? So we can say the partial pressure of the oxygen is equal to the total pressure times that mole fraction. Substituting 250 torr times 0.211 for the mole fraction is 52.8 torr. Now, stoichiometry of gases. Gases that are produced by chemical reactions end up following the rules of stoichiometry and how much gas is formed in terms of moles, but we can also then calculate pressures and things like that of them with the gas laws like we would for any other gas law problem. Show you how that works. Let's look at a gas forming reaction. This will include a little stoichiometry, so you can go back and look at my stoichiometry video if you'd like a refresher on that in a little bit more detail. Calculate the amount of hydrogen gas in grams, which will be from stoichiometry, and liters, which will be from gas laws, that can be formed when 8.5 grams of magnesium metal is completely reacted with hydrochloric acid at 24 degrees Celsius at an atmospheric pressure of 770 torr. And we have the balanced reaction, magnesium reacting with 2 HCl's to form magnesium chloride and hydrogen gas. What we're going to be interested in is the hydrogen gas because it's the gas. So let's do some converting. We need to know the molar mass of hydrogen to get the mass, so let's go ahead and do that. 2 times 1.01 grams per mole is 2.02 grams per mole. Temperature 24 plus 273 is 297 Kelvin. 770 torr divided by 760 torr per 1 atm is equal to 1.01 atm. So that's our conversions. Now let's actually work the problem. So if we take 8.5 grams of magnesium from the periodic table, 24.31 grams of magnesium per 1 mole, that gives us moles of magnesium. Since the stoichiometry on this reaction was 1 to 1, there's 1 mole of magnesium to 1 mole of hydrogen. And we find everything will cancel but moles of hydrogen, and we got 0.350 moles of hydrogen. Now, if I were just working a simple gas law problem and I hadn't been asked for mass, I would just stop there because I need the moles for my gas law problem. That's my N. But since I was also asked for mass, 3.5 moles of hydrogen times 2.02 grams of hydrogen per 1 mole will give us 0.706 grams of H2. Even though I truncated for significant figures there, I did hold the whole number in my calculator to prevent rounding error. So going back to our previous response of 0.350 moles of H2 and our answers from the previous slide, we're going to use our ideal gas law to figure out the volume of gas. So V is equal to nRT divided by P. Plugging in, we got 0.350 moles times 0.0821 liters ATM per Kelvin mole, that's our gas constant, times 297 Kelvin is our temperature, divided by 1.01 ATMs, which is our pressure. Everything's going to cancel but the liters, and we have 8.45 liters of hydrogen gas produced under these conditions. This has been a brief tutorial of the ideal gas law, Dalton's law of partial pressures, and a little bit of reaction stoichiometry producing gases.